Hello, everyone. Can you all hear me in the back? Can you hear me? Wave? Yeah? Nobody's waving in the back? That's okay. Hi, I'm Jan. I'm a front-end engineer working at SoundCloud. I'm from Berlin. On Twitter, you can find me at the DevDon or on GitHub as Jan Monschke. I have a very hard to pronounce last name. I'm sorry. It's my parents' fault. Today, I want to talk about collaborative algorithms. Not because it's a topic that I like that much, but because it's something that I needed and I wanted to understand while writing my thesis. So because I recently finished my master thesis, I will do this talk kind of like in the fashion as a lesson in university. So I invite you to all go back in time and enjoy my lesson. Today, I will base all the knowledge in this talk is based on 3 different papers. One by Neil Fraser, the main algorithm. One by observations by Sun et al. About algorithms. And my own master thesis, because I need to dog food my master thesis as well. So when we talk about collaborative applications, what do we actually mean? And I don't mean this. Like, you have 2 people, they work on a problem, and then they use the keyboard at the same time, and it's double fast. This is not what I mean, and it's totally not real. This will never help you with any problem. If you're capable of doing that, talk to me, because I want to learn that. What I mean with collaborative applications is stuff like Google Docs, Wunderlist, Trello, which we all love, where many people can work on the same page, on the same data structure at the same time. And they allow us to work together. So, quick question. Who in here has built a collaborative application before? A couple of people. You see, that's what I mean. Like, the algorithms are so hard, and if it would be much more understood, everybody would program that. And the people that did this, what did you use to synchronize stuff? Just yell in the room. Sockets. Great one, great one. WebSockets are the standard that we will use in this presentation as well. But like, how do we, this is like how we transfer state and not how do we synchronize states if we have several people working at the same thing. So we need some requirements for our algorithm, and this is getting super lessony right now. First, our algorithm needs to support convergence. Convergence means that due to latency on the web, 2 users and 2 browsers will at some point have 2 different versions of the same document, because the web is not really real time. So our algorithm needs to support that. There needs to be conversions, but it also needs to go back. Then the algorithm needs to preserve intention. What does that mean? The intent of a change needs to be preserved. That means when I type in a text field on my local browser, this intention should happen in the same time on the other side for the remote people, and in the same fashion. So if I type cats, and another person is receiving my stuff, it should also say cats, and not CTAS, so it needs to be in the same order. This is like a little diagram to show you what could happen. So we have user A, it has this string, and user B has this string. At the same time, we do an edit. User A inserts an F in the beginning, and user B deletes the H. And then these changes are transferred, and we both result in 2 different versions of the string. So the causality, or like, I wanted to add something here, but actually it got deleted. So the causality of my changes is not preserved. Oh no, this was intention. Sorry. Causality is something different, because the order of the changes needs to be in the same time as well. And how can we achieve that? There's the easiest way to synchronize something is to lock. So we work on the same ticket in Trello, and I just disallow you to edit the same thing. This is a very pessimistic approach, because while editing, the object is locked for other users, so it's not really collaborative. It's just, you cannot break things because we're not editing at the same time. So you can do that like, oh, if we work on the same card, maybe I'm editing the description and you add the title. So we could add like a feature to allow, okay, I can only add the title, you can add the description. But still, this is not really real time and collaborative. And also, we need to handle all that state, you know. And on top of having this lock algorithm, you also need to save all the state on your server. And it needs to be synchronized as well. So all the users need to know about which objects are locked, and that you have to write that as well. So this is not a good approach, but there is a set of algorithms out there since pretty much the 80s, and they are named operational transformation, which is the magic that powered Google Wave. Who remembers Google Wave? Yay! Now Google Docs. So it's the same technology that is used to synchronize stuff. And how it works. So let's say we have the example. I'm typing cat, and each operation, like every single character that I type, is sent to the server. And the server then applies this to a master document and distributes all the changes to all the peers. The problem is, as I showed before, what happens if we type at the same time, you delete something, I add something, how can we do this? How can we prevent this from happening? And the problem in operational transformation is that the concept is very easy, but you always run into these problems where you need other algorithms to solve this problem. So in order to prevent this problem from happening, you have to implement the sync system and then the fixed synchronization system, and then this might be broken, and then you might need another system that needs to fix this system. So it's very hard to understand, and a lot of work is required when you want to write such a system from scratch. But there's already a JavaScript library out there which is called Share.js, and it's pretty awesome. So I could have just used that. But Share.js locks you into using MongoDB. Don't get me wrong, I'm not a hater on MongoDB. I used MongoDB very often, but as it happened to be, I prefer another database, or I want to use whatever database. So there's no way you can use another database. There actually is a way. You can implement a very complicated interface, but if you don't understand the algorithm, you cannot implement this interface. So you basically could write the algorithm yourself and build your own database interface. So it's kind of pointless if you don't want to use MongoDB. Yes. Another problem with Share.js is there's like version 0.6 out there, which is super stable, but the people, like the authors say, don't use it. It's not as good as version 0.7. But version 0.7 doesn't have any documentation. So you're kind of stuck in the world where you have to read all the code and understand the algorithm, even though you wanted to prevent that from happening. And this is just a side note to the authors. It's very tiny. Joseph Gentle, the author, shouldn't get me wrong. I like his library, but it didn't work for me because I didn't want to learn all these algorithms. I wanted to learn one algorithm to make it right, which is called Differential Synchronization. And I don't have a cool punchline for that one. So instead of sending each operation, like each keystroke, to the server, this algorithm works in a way that I have a document, and I change something at the document, and I send this change to the server, not a keystroke. So the server then applies them to a master document and distributes the changes to the peers. Sounds very similar, but the fact that we're not sending operations, but diffs and patches makes a big difference in the end. So every peer is constantly via WebSockets connected to a server, and they start synchronization cycles. And how it works is that. This is the guy, Neil Fraser. He's explaining the algorithm for you, and I hope you're all watching, because there will be a test, right? So he's adding like, oh, we have this side, and with that side, and there's like a circle around. Stuff is happening here and here, but in very soon, he will remove that part, and it all makes sense. So this guy, Neil Fraser, he wrote this great paper on this algorithm, but he also published a 1-hour YouTube video on how his algorithm works. And to me, the best way to understand this is to watch him at a board and like explain it. So you can afterwards watch it on YouTube. I highly recommend it. It's very entertaining because he explains a lot of things very easily. And this is what I'm going to do right now. So I hope you're all ready and you got your textbooks out. The algorithm is structured in a way that you have a client side and you have a server side. The server, let's say you connect to Google Docs, has a master document, which is the server document over here. Let's make a scenario. Let's say I connect. The server is sending this document to me, and what I do as a client, I create a client document and a shadow. These are the same documents, basically copies, deep copies of these documents. Now, this document is pretty empty right now. It only says cat, which is kind of nice, but I want to improve it, so I write cats. At the moment that I change something, the client is creating a diff of what I'm editing to the document. So one document is what the server says, and one document is what the client has. So one says cats, and the other one is still at the state of the server and says cat. So if I diff that, I get add an s. So this is then put on a stack, and this stack is sent to the server. The server, remember, has the big document, the master document, but the server also has a shadow. I don't know why he's using the word shadow. It's basically a copy, but he has a copy of documents from all the clients as well. So this is like add an s to the cat. This says cat. This says cat. And then what I do is I take this patch and I apply it to the server document, and I apply it to the copy of the client's document. Everybody still with me? Raise your hand if you're not. Ha, gotcha. Cool. So at this point, we have cats written here and cats written here. And then what's happening in the cycle automatically, the server is doing a diff of these documents and is sending me the diffs back. And I will apply them to my documents. What that does then is, since we have cats here and cats here, the diff will be empty and I will receive an empty diff and nothing will happen. But remember, we connected to this Google Docs thingy where maybe another person was editing. And this person edited this document to say, oh, to cat without an S. It's like a typo. So at the same time, while I was writing cats, this person was writing to. So the server document actually says to cat. What I'm sending over here is add an S, and we add an S to this, it says cats, and we add an S to this, and it says two cats, because essentially we have the word cat and we add an S to this, because the diff set take the word cat and add it in such a way that you add an S to the word cat. So what we then have here, cats and two cats. What's happening then is the server will create a diff, and the diff between cats and two cats is just two. So add the word to in front of it. This diff will then be sent to my client, and then on my client I will have two cats and two cats. So the state that another user has edited is then automatically transferred to the client. And that is basically how it works. Everybody cool? Any questions now? Yes. Oh, can we do questions now?
Hello. So the question is, the tool that I use is Git. So it uses diff algorithm. So it have conflicts. What about conflicts in this situation?
Okay, so what happens if we have a conflict, basically?
Yes.
Yeah, so we're not using Git for diffing and patching. We're using a fuzzy algorithm for patching. Fuzzy means that if there's a conflict, this algorithm is still able to produce a valid document from that. And so this fuzzy algorithm will always create valid documents. But what happens if we have a conflict? A conflict to me would be something like, let's go back to userland. User A has the word cat, and user B has the word cat. User A says it should be called cats, but user B deletes the word. Then how can we apply the S to the word that is not there anymore, right? So what the algorithm is doing here is one version wins, because there's no way that the algorithm can find out what should happen. And imagine for yourself, if you're editing a document and you both add the same word, what do you expect to happen if the word is deleted? It should still be a valid document. So either the delete works and the word is gone and only the S is there, or the delete does not work and we add the cats still. Because this is a conflict that actually the two people editing have, and they should find a way to make this document work for both of them. Does this kind of answer your question?
I think yes.
Okay. We have another question. Oh, wow, another one.
Another question is, how does the diff algorithm work if I have some more complicated structure than text, like...
You mean JSON? XML?
For example, when
Yes.
I have objects that are inserted into
Yes.
each other.
It works the same way. There are many diff algorithms for JSON and XML out there. And this algorithm is actually independent from the implementation of your diff or patch. It just needs you to have a valid diff or patch. And you can use whichever algorithm works for you, basically.
Okay, and the other question, do we have server shadow documents for each user we have
Yes.
in the system?
Yes.
And the diff is built between the master version that has only one version in the system and the other that belongs
Yes.
to each user?
Yeah.
Okay.
So what's not really clear from this thing is for every user, the server has one of these. Yes. I should mention that maybe next time.
I have a lower level question. How does it know that a cat is a cat? And if the cat was moved in the text, how does it know that it is the cat that needs to be edited?
Yeah, this is a different problem. This is a problem that the diffing algorithm has, because the diffing algorithm needs to make sure that it is able to track this. And the algorithm here is not telling you how this diffing algorithm should work, but it's a different set of algorithms that we have to look at. But I don't have the time to explain this here. But the resources for finding out how that works is also in this paper. Okay, some questions are cleared. I hope we're all still in the big picture. So I call this YouTube-driven development, because you just watch a YouTube video and then you understand how it works, right? This algorithm is much easier to understand. You know, like the circle is quite easy. You see, oh, I send my patches here, and like I can use whatever algorithm for patching and diffing, so I don't need to care about that. The cool thing is it can sync arbitrary data. I talked about text here, but actually I never used it for text. I only used it for JSON and XML. And if we look back at conversions, intention, and causality preservation, it all does that for you, because all the changes that are done on the documents are always based on the previous version that you had before. So the context is always preserved in all ways. And we can have convergence, means we can have two different documents at the same time, but we will all come back to the same document in the end, no matter which kind of document it is, though. And the cool thing is, you don't need to implement that in JavaScript anymore, because I did that for you for my master's thesis. So you can just go npm install DiffSync. It has a client and a server implementation. It's database agnostic, yay! I use CouchDB, yay! The backend integration is super simple, and the front-end integration as well, because it's basically event-based syncing. So you can use that in React Backbone or Angular or Ember, whatever. I'm not sure about Ember, never tried it out. So you ask, how easy is it? And I will show you. So the server implementation basically looks like this. Oh. Can you see that? So you only create your normal Express server, a Socket.io server, create this DiffSync library, and say, oh, I want to only persist to in-memory, because I don't need a database right now for this test. And then you hook it up to your server, and that's it. You don't need to care about anything else, because saving the data and everything is encapsulated in this data adapter, which could connect to whichever database you have. So there's a CouchDB adapter that connects to your CouchDB. And how do I do this? If you want to write your own data adapter, it's pretty simple, because you only need to implement two functions, and one is called getData, based on an ID, and storeData, based on an ID. So this is all that your backend needs to implement in order for this algorithm to work, because all the transforms of data is done in this library itself. A bit trickier it gets when you have the client implementation, though. Where's the plus? Yeah. You create the library, hook it up to your WebSocket, and then that's it. And you know when it's connected, like a WebSocket is not an open connection right away, so you need to wait until it's done. And then you can get the data from the client. And from then on, you will always receive a synced event when anything happened on the server. And depending on what kind of front-end architecture you have, oh, this does not go good. Depending on how your front-end architecture works, for example, for AngularJS, you can listen to local events and then sync. And this sync will send all the changes up to the server that you did in your front-end applications. In React, it's even much easier, because you just need to wrap it into in its own component. And in Backbone, it's you listen to change events. It's basically the same thing. So whenever you have a synced event, you get an update. Whenever you say sync, it will send all the updates. It's like 3 methods that you need to implement real-time data. So a little demo time. If you all want to go to this URL, it's a Heroku app, so it needs like 2 minutes to start, because I haven't used it in a while. It's diffsync-todos.herokuapp.com. It's already there. It's already there. We have 2 connections. You can go to test to-dos. And this is my to-do list for today. There's not much on it, but we can add some more. Are there any more people connected? You can add stuff. Also, there's no way that there's XSS attacks possible, I think. I'm escaping because I don't trust you. We all learned that in the first talk. And have Great. Lunch on the to-do list. And this one is almost done. I think I can say it's done. And then, yeah, everybody can add whichever stuff they want to do. And this is like a simple to-do list application. The code is open source. You can have a look at it. And this all works with WebSockets. And how many connections do we have? 13 connections. It's on a single machine, and it goes up to 100, or depending on how much your Heroku cluster allows you to have. And yeah, 17. There's more. Okay. Stress test. No. Okay. Demo time. So I was introduced as being kind of like a musician. I'm not really a musician. I'm just passionate about music. Do we have sound, by the way, from the computer? No. Okay. What you can do with this is build applications like, oh wow, YouTube. Like what I built with this in my master thesis is a collaborative music editor, like if you know GarageBand or Ableton. This is pretty much the same thing. Like this is browser A, this is browser B, and whatever you do here, it happens here. And this is a fun way to have like bands collaborating online, or like if you want to jam with your friends, and it has like video chat in it, so if your band members live far away, you can still have fun together. Yeah, this is what you could use it for. Where is it? Oh no, I closed it. Okay. And that's it. Thanks. You can find me on Twitter as the Deftone, on GitHub as Jan Monschke, and the slides are online under my domain /diffsync-presentation. And yeah, I highly recommend checking out the library. It's like, the code is quite easy to understand. Read the paper, it's pretty cool. And if you're still a fan of reading master theses, you can try to read my master thesis and give me your opinion. Not many people have read it, so no pressure on reading that. Okay, yeah. Any questions?
Вы можете задавать вопросы по-русски, если что, я буду переводить. Только микрофон возьмите, пожалуйста. Микрофон.
Ян, спасибо огромное за доклад. Реально полезный инструмент. Вопрос такой, а сколько одновременно разработчиков может в нем работать?
Повтори, пожалуйста.
А сколько одновременно разработчиков может пользоваться этим сервисом?
Thanks for the talk, Jan. And how many developers can use the service at the same time, simultaneously?
How many developers?
Yeah.
Ну да, how many developers?
Well, it's the limit is pretty much the limit that your box can connect people to, plus or minus whatever the algorithm needs. But like the overhead of the algorithm is very minimal, because the diff operations are very minimal, or even for big data structures, because small diffs are easy to handle via the network.
Thank you.
You're welcome.
Hello, thank you.
Well, I'd like to elaborate the. Sorry.
Okay. I have a question about the DiffSync algorithm. You talked about text synchronization, and as far as we speaking about synchronization, the most important feature is merges, conflicts, and as far as I understood, the algorithm produces only one result that it thinks is appropriate. But when we type text and everything seems fine, and suddenly another version arrives completely different, and we lose all our text, is it okay? And is it supposed? Do you mean that a client should be responsible for handling these situations, or is there any methods to handle it in your framework on the server?
For now, the library that I built only comes down to one version. There's no client resolving of conflicts, but it always depends on your application. If your application has important data where we need to make sure that conflicts are resolved properly by humans, because computers cannot make sense of the data, there is in this algorithm even a way to send conflicts to a client, and then they can work it out. But for now, only one version. But I think, depending on the application, it's very important that you do manual conflict resolution. Yes.
Okay, thank you.
Sorry, here I go again. So my question was actually, can you estimate the time and space complexity of the algorithm in regards to the simultaneous users or the data? Because editing that sound file can take pretty much space.
I didn't get the last part. It was a bit.
Ты можешь задать по-русски?
Just louder.
Just short. Okay. So what's the time and space complexity of that algorithm? Because editing that large sound file by multiple users can result in memory consumption or something. So how do these things scale?
So it's hard to say. It depends on the diff that you're using, because the diff is the main work that the algorithm is doing. The algorithm itself is just a structure for sending the diffs. So it depends on the complexity of your algorithm for diffing. Does that make sense?
Yeah, thank you. But that application you showed for editing music file. So.
Therefore, this was pretty simple because I was only using JSON data structures that represent operations on a file. So I'm not writing a diff algorithm for files itself, but you have one file, and then if I want to change the length, like this, I want to make it shorter, the audio file, I just say, start here, end here. It's just another field in JSON, so it was very, very, very simple.
Oh, I see, that makes sense. Thank you.
Hi, how much overhead adding for each additional version in storage? I mean, if additional versions, shadow versions are stored in CouchDB.
Are you saying how many versions are saved, or how?
Yeah.
Only, you can tweak it maybe, but for now only one version. And if we go back, take some time. For now, one here for each client. These are two versions of the document. And there's one thing that I never talked about is the backup file. So for each user, you have the normal file and the backup file. So if anything goes wrong here in transmitting and sending, we can always fall back to the latest stuff. It has the algorithm has a way to find out if changes arrived or not via hashing, but it's basically two versions. So undo is something that you need to do on your clients.
So these versions do not survive restart of server. Shadow versions, I mean.
Maybe, I don't know.
If you restart server, do the server shadow survive?
It depends on if you persist or not.
Yes, and in your implementation,
yes, it's persisted.
Okay, thank you.
I got a question about re-implementing the algorithm in the other language other than JavaScript. Is it hard to re-implement on the server side in Java or any other language?
No, it's language agnostic. So the algorithm was implemented the first time in Python with a JavaScript front end, and my backend is written in JavaScript. But as the only connection between server and client is a WebSocket connection, anything that can speak WebSockets on the server could be your server language. So if you have a Python library for WebSockets or a Java library for WebSockets, you can build it. But you need to write the algorithm again on that side.
Okay, am I correct that the main diff algorithm that used both on the client and the server side are just plain diffs between two strings, basically? So if you want a diff between two structures like JSON, then I have to serialize it into a string, then build a diff, and then build up.
No, not really. In my libraries, I'm using a JSON diff algorithm that is diffing objects and not strings.
So it's tree, fair
it's
tree comparison,
yes.
comparison algorithm.
It's a tree diff algorithm. That on top of only doing JSON, if you have long text in your JSON, like a long description field, this algorithm also takes care of merging long text.
And that diff algorithm is built into your library,
yes,
actually?
It's built in there.
Thank you.
Okay,
Еще вопросы?
The shadow copies, are they the same size that the original document?
Yes.
So for every user, I
Yes.
have
Well,
the same size?
Yes. In my implementation, which is kind of basic, they are the same size. If you are a fan of immutable data structures, you could build it in a way that these are only change trees of the original file, so that you would have like a much easier, much smaller data problem there.
Okay, thank you.
How do you understand the order of events?
Sorry?
How do you understand the order of events?
The order of events is because every edit that is done is always going one way. So the order of events here is only in one direction. So there's nothing that I can put in there. So because this is always the client document, a copy of the client document, and this is always the client document, and the diff is applied on the client document, the order is preserved in this document. And then, because it's a semantic diff, depending on your implementation, the order will be preserved here and here.
And what comes first to the server is the first diff, right? If what the first comes to server is the first diff, right?
Yes, depending on in which part, yes.
Right.
Еще вопросы? Еще вопросы? Окей. Все. Thank you, John.